Hello everyone, this is the second video of lecture 6. In this video I'm talking about the weak duality theorem and strong duality theorem and also the relationship between the solutions of primal and dual problems. First, weak duality theorem. Assume that we have two problems, primal and its dual. The primal problem, it's a maximization problem, and the dual problem, it's a minimization problem. Maximization of CTX subject to a series of constraints, AX less than or equal to B, X's are non-negative variables. The dual problem is BTY, B transpose Y, subject to A transpose Y greater than or equal to C, Y greater than or equal to 0. Any feasible solution to the primal problem, let's have it as X. Any feasible solution to the primal problem, assume that Y is any feasible solution to the dual problem. Any feasible solution to the primal problem, which is a maximization one, is less than or equal to the solution of the dual problem, which is a minimization. So the objective value for any feasible solution for the maximization problem is always less than or equal to the objective value of the minimization problem. Now let's see what is strong duality theorem. Here in weak duality, we talked about any feasible solution for both X and Y. The objective value of maximization problem is always less than or equal to the objective value of all feasible solutions to the minimization problem. A strong duality is talking about the optimal solution. If X is optimal to the primal and Y is also optimal to the dual problem, X for maximization problem, Y for minimization problem, then the objective value of the maximization problem equals to the objective value of the minimization problem. Weak duality, strong duality. So when you found the optimal solution for maximization problem, and we also find the optimal solution for the minimization problem, the objective value of them are equal. This is the strong duality. There is a proposition for a strong duality, and it says that if X and Y are feasible solutions to the primal and dual, X is feasible to primal, Y is feasible to the dual, and the solution of the objective value of them are equal, then X and Y are optimal. So X is feasible to the primal problem, Y is feasible to the dual problem, and you see that the objective value of the primal and dual are equal, then you can conclude that X is optimal to the primal, Y is optimal to the dual. So, in summary, I can say that weak duality says that X is feasible to the primal, Y is feasible to the dual problem. I can conclude that the solution of, when I say that feasible to primal, means that I assume that it's maximization problem. I can conclude that CTX, the objective value of the maximization problem, is less than or equal to the objective value of the minimization problem. Strong duality says that if X is optimal to the maximization problem, Y is optimal to the minimization problem, we can conclude that the objective value of these two problems at those optimal points are equal. And the proposition from the strong duality says that if X is feasible to the maximization problem, Y is feasible to the maximization problem, and the solution of maximization problem equals to the solution, the objective value of the minimization problem, we can conclude that X and Y are optimal to the primal and dual. There are some relationships between the solutions of primal and dual. If you remember that an LP has three possible outcomes. Three possible outcomes of LP are these. It can be optimal, an LP can be unbounded, or infeasible. These are three possible outcomes after solving a linear programming problem. Let's see what are those relationships. Assume that you found an optimal solution to the primal problem. What is your guess for the dual? The outcome of dual can be optimal, unbounded, or infeasible. From a strong duality, we know that if X has an optimal solution, if the primal problem has an optimal solution, which is X, then Y should be optimal too, and the objective value of them is the same. So dual definitely will be optimal. What about the relationship between primal and dual if the solution to the primal problem is unbounded? Then the solution to the dual will be infeasible. You cannot have both cases as unbounded, and since there is no solution to the primal, it's unbounded, you cannot find any solution to the dual, so it should be infeasible. What about having an infeasible solution to the primal? Then the dual can be unbounded, like this one, unbounded infeasible, infeasible unbounded, or infeasible. So you can have both as infeasible, but you cannot have both as unbounded. One of them is unbounded, definitely the other one is infeasible. One of them is infeasible. For the other problem, you cannot say that it can be both. It can be either of them. It can be unbounded or it can be infeasible. Let's solve some examples. These are the examples of slide 21. The primal is maximization of x1 plus 2x2, 2x1 plus x2 less than or equal to 6, x1 plus x2 less than or equal to 4, x1 and x2 greater than or equal to 0. I would like to solve this problem by graphical method. I'm drawing the first constraint. 2x1 plus x2 equals to 6. So for x1, I will have 3. For x2, 6. This is x2, this is x1. Let's connect these 2 points to draw the line of the first constraint. It's less than or equal to 6. You just need to try 1 point, for example 0 and 0. 0 plus 0 is less than or equal to 6, yes, so it should include 0 and 0. This is the feasible side of this constraint. x1 plus x2 less than or equal to 4. This is 4, this is 4. I'm going to connect these two as well. For the second constraint, again the direction of the feasibility side is this way. So the common region that can satisfy both constraints is here. The objective function is x1 plus 2x2. Which one of these corner points are optimal? Is optimal. x1, the coefficient is 1. For x2, the coefficient is 2. So start at any point 1 unit in the direction of x1, 2 units in the direction of x2, and draw the direction of improvement for objective function. If you draw the objective function line which has right angle with this row, you can improve your objective function in this direction. So what is the last point in the feasible region that you cannot go further than that? It's here. So this is your optimal point, which is 0 and 4. The objective value here, it's 0 plus 8. It's 8. So we have an optimal solution to the primal problem. Let's check its dual. For drawing the graph and solving the dual, we need to write down formulate the dual problem from this one. It's maximization, so the dual will be a minimization problem. The right hand side coefficients are 6 and 4. So the objective function coefficients in the dual are 6 and 4. 6y1 plus 4y2. Subject to A transpose. So any column here will be a row here. The first column coefficients are 2 and 1. 2y1 plus y2. The second column 1 and 1. 1y1 plus 1y2. The right hand side of the constraints for the dual problem are the objective function coefficients 1 and 2 respectively. x1 and x2 both are non-negative variables, so we need a natural direction for the minimization problem which is greater than or equal to constraints. The first constraint here is natural for maximization, so x1 is greater than or equal to 0. The second constraint is also natural for maximization problem, x2 is greater than or equal to 0. Let's draw the graph of this problem and solve it. y2, y1. The first constraint, 2y1 plus y2 equals to 1. y2 will be at 1, y1 will be at half. So if you draw the line of this constraint is this. Just try one point. 0 plus 0, is it greater than 1? No. So this is the feasibility side of this constraint. It doesn't include 0 and 0 because it doesn't satisfy the constraint. 0 plus 0 is not greater than 1. y1 plus y2 equals to 2. So we have this line. Again, it's a greater than or equal to 2 this way. I'm sorry, these are y, not x. Our variables here in the dual are y's. y1, y2. y1 is greater than or equal to 0. y2, this is y2 greater than or equal to 0. y1 greater than or equal to 0. Where is the common region? It's here. Let's see what is the improvement direction of the objective function. 6y1 plus 4y2. It's minimization, so I'm gonna multiply it by -1. Minus 6y1 minus 4y2. So this is the improvement direction. The objective line will be improved through this direction. Which is the last point? This one. What is this point? It's 0 and 2. The objective value at this point is 0 plus 8. As you see, we have an optimal solution to the dual, which is 8, and also an optimal solution to the primal, which is 8. So, whenever you have an optimal solution to the primal problem, you will have an optimal solution to the dual. This is our first example. Let's solve another one. It's a minimization problem. Minimize negative 3 x2, x1 greater than or equal to 2, x1 minus x2 less than or equal to 1, x1 and x2 are greater than or equal to 0. Let's draw this graph. x2, x1. The first constraint, x1 equals to 2. So it would be this. x1 greater than or equal to 2. So which is this? This feasible side, the feasible side of the first constraint. x1 minus x2 less than or equal to 1. So one point will be 1 and 0. Another point will be 0 and negative 1. What is the feasible side, this direction or this direction? Just try one point. 0 minus 0 is less than 1, yes. So this is the direction. x1 greater than or equal to 0, x2 greater than or equal to 0. The common region will be here. The region is unbounded. We need to check that if the solution to this problem is unbounded too or not. Can be this point or being unbounded because we have just one feasible coordinate point. Its minimization of negative 3 x2. It's equivalent to maximization of positive 3 x2. So the improvement direction is this. Is there any limitation to prevent us to go further and improve the objective? No, it's unbounded. So the solution to the primal problem here is unbounded. Based on this relationship, I expect to have an infeasible solution for the dual. Let's check it. The dual of this problem is going to be a maximization problem. Two constraints, so I'm going to have two variables, y1, y2. The right hand side of the primal problem are the coefficients in the objective function of the dual, 2 and 1. The constraints, the first column coefficients, first row, 1, 1, y1 plus y2. The second constraint, 0 minus 1, 0 x2, negative 1 x2. So minus y2. The right hand side will be the coefficients of the objective function in the primal, 0, negative 3. For the direction of the constraints, you need to see the variables in the primal. Variable x1 is a non-negative variable, is greater than or equal to 0, so the first constraint will be natural for maximization problem, less than or equal to 0. Also, the second one is a non-negative variable. We need a natural constraint in the maximization problem, which is less than or equal to. For y1 and y2, to see if they are free, greater than or less than or equal to 0, we need to see the constraints in the primal. The direction of the first constraint in the minimization problem is natural here. So y1 is greater than or equal to 0. The second constraint in the primal problem is not natural for the minimization problem. So it's less than or equal to 0. Let's draw the graph of this problem. y2, y1. The first constraint, 0 and 0 is 1 point, we need another point. Assume that y1 is 1, y2 is negative 1. So this point. What side of this constraint is feasible? You need to try some points. For example, 1 and 1, this one. 1 plus 1, is it less than or equal to 0? No. So it should not include 1 and 1. This is the feasible side of this constraint. Second constraint, y2 equals to 3. Assume that we multiply it by negative 1. y2 greater than or equal to 3. These are equivalent. If you multiply both sides by negative 1, then the direction of the constraint will be changed too. So y2 is greater than or equal to 3. y1 is greater than or equal to 0. So the positive side of y1 axis. y2 is less than or equal to 0. So we are here. y2 should be less than or equal to 0. All points here, y2 is negative. This is y2 axis, so y2 here is negative. Can you find any common feasible region here? No. There is no feasible region. It's infeasible. So, as you see, when the primal problem is unbounded, the dual is infeasible. Unbounded, infeasible. Let's solve another example. The primal is minimization of x1 minus x2, x1 plus x2 less than or equal to 1, x1 greater than or equal to 3, x1 and x2 are greater than or equal to 0. Let's draw its graph. This is x2, this is x1. The first constraint, x1 plus x2 equals to 1. 1, 1. It's less than or equal to 1, so this direction. x1 greater than or equal to 3. x1 is greater than 0, x2 is greater than 0. Can you find any feasible region here? No. So it's infeasible. From this relationship, I expect to have an unbounded or infeasible solution for the dual. So let's try it. Dual will be a maximization problem. Two constraints, two variables here. 1 and 3, right hand side of the primal, will be the objective coefficients here in the dual. y1 plus 3 y2. First column, first row. y1 plus y2. 1, 0. y1. Objective coefficients 1 and negative 1 will be right hand sides. Let's look at the variable here to see the direction of constraints here. Both of them are non-negative variables, so we need natural constraints for maximization problem. What about y1 and y2? The first constraint is not natural for minimization, so it's less than or equal to 0. The second constraint is natural for minimization, so it's a non-negative variable. Let's draw its graph. y1 plus y2 less than or equal to 1. y1 is less than or equal to negative 1. This is the second constraint. This is y2, this is y1. y1 is less than or equal to 0. y2 is greater than or equal to 0. Where is the common feasible region here? This is our feasible region. The region is unbounded. Let's check the objective function coefficients to see if our solution is unbounded or one of these corner points. Its maximization of 1 and 3, 1y1 plus 3y2. 1y1 in the direction of y1, 3 in the direction of y2. So the objective function will be improved in this direction. Is there anything that limit us to prevent us to improve the objective function? No. Here at this point we have an objective value, but you can go further, you can go beyond that, so it's unbounded. Infeasible, unbounded. Let's solve the last example, the last one. Its maximization problem: x1 plus x2, x1 minus x2 less than or equal to 2, x1 less than or equal to negative 1. Both variables are greater than or equal to 0. x2, x1. x1 minus x2 is less than or equal to 2. So this is the line, 2, negative 2. 0 and 0 is less than 2, so it should include point 0 and 0. x1 is less than or equal to negative 1. Both variables are non-negative, so we are in the first quarter of this graph. Is there any feasible region? No. It's infeasible. Let's solve the dual. It's a minimization problem. Again, it has two variables because we have two constraints in the primal. 2y1 minus y2, 2y1 minus y2. The first constraint coefficient will be the first column coefficients in the primal, y1 plus y2 minus y1 plus 0 y2. Right hand side are 1 and 1. The direction of the constraints will be natural because both variables here are non-negative. So natural means that greater than or equal to for a minimization problem. y1, y2. Here we have both natural for maximization, so both are greater than or equal to 0. y2, y1. The first constraint is this: y1 plus y2 greater than or equal to 1. So this is that direction of the feasible side of this constraint. The second one, negative y1 is greater than or equal to 1. I can write this as y1 to have it easier to understand or draw. y1 less than or equal to negative 1. y1 is greater than or equal to 0 and y2 is greater than or equal to 0. Can you find any feasible region here? No. It's infeasible. So infeasible, infeasible. The previous example, the primal was infeasible, the dual was unbounded. The second one was unbounded, infeasible, and the first one both had optimal solutions.